Hello and welcome to the first session of our FEA Master Class here at SimScale. I'm happy to see so many people who have joined for our first session today. And before we actually start to dive into our journey of finite element analysis, I would like to make sure that everyone can hear me loud and clearly. In the tool we are using to broadcast this webinar, you will find a button called Raise My Hand. Please click this button in the case you can hear me loud and clearly. Great, I see a lot of hands. In the case for some reasons the audio stream should drop, you can also use our toll-free audio service numbers. You will find them here on the slide. Just choose the number which is related to your location. As I mentioned, they are toll-free. And then enter once you're asked the access code for 10350-387. Great, so let's take a look at our today's agenda. First of all, we will do a very crisp introduction to the idea of this workshop series and also about what we will talk today. After that, we will went very quickly through the very fundamentals of FEA just to make sure that this kind of knowledge is existing for every one of you. And in the case, just a general thing, you have questions. You can write them in our question window, and we will try to answer the questions on the fly during the session or at the end during our Q&A. Yes, today, yes, it's our first webinar, so let's just quickly summarize the most important things. Yes, this webinar is part of our workshop series, the Finite Element Master Class, and the idea is to help, let's say, intermediate users who already gained some experience with FEA and SimScale to improve the quality of your results. And it will work like this. We will have every week a session focusing on a different aspect. So this week we're going to talk about meshing and everything which is related to meshing in model preparation. And after this webinar, you have like 1 week to prepare and submit the homework. Every session comes with a corresponding homework, and if you submit all 3 homework assignments, you will get a certification of participation for this workshop. Since a lot of questions are asked frequently, I would just like to go through them. First of all, we will record all the workshop sessions, so in the case you cannot make it for a webinar, don't worry, you can access the recording 1 day after the webinar took place. And in the case you are new to SimScale or a web-based simulation environment, you can create all the simulations yourself. Every homework is related with the simulation assignment you have to do, and in the case you need support, you can just visit our forum on forum.simscale.com. We have there a dedicated section just about this workshop series. Let me show it. So on simscale.com, and if you go to the section SimScale Workshops, you will find FEA Master Class. And in the case you have a question, just use this forum to reach out to other participants of the workshop and also to the SimScale employees, which will be happy to help you. In the case you want to learn about something, about a topic which may not covered here, not covered during the workshop, we have a lot of free learning resources which you will find on our webpage, simscale.com. Well, okay, then let's dive into our today's topic. As I mentioned, today we will talk about meshing, and therefore let's first of all talk about the general process of finite element analysis. First of all, what is FEA? So FEA stands for Finite Element Analysis, and it basically refers to a technique which is used to numerically solve particle differential equations. Yes, you might hear about this kind of equation at school or in university. Differential equations are relating the change of something to the quantity itself, and they are used a lot in physics. A very easy example is maybe Newton's law of motion, which relates the force on the moving body to the product of acceleration and mass. And acceleration is a change of velocity and therefore the change of location. And you will wonder how simple some of the equations are which are used for finite element analyzers. And the basic problem we are facing with is that the equations which I was describing, for example, the reaction of a solid body, they are known for at least 100, 200 years. But unfortunately, this kind of equations can only be solved for very simple examples analytically, and there is no analytic solution for, let's say, general problems. And in the end, the idea of FEA is to solve a continuous equation which we cannot solve for a continuous domain by discretizing it using functions. And this function, this discretization, gives us a very good approximate solution. And that's in the end how FEA works. And basically what we are doing, we are taking this partial differential equations as PDEs, which we cannot solve, and we are transforming them into a system of linear equations which we can solve. And since in the last years computational capacity has grown, we can now use these computers to solve the linear equations. And basically what I talked about now was very general, but let's try to make this more vivid, taking a look at a very simple example. Let's say we have a hook like this, and we want to analyze how this hook will deform and which stresses will appear if we put a load on this hook. For example, in the case this hook is used to lift a heavy weight. And in reality, we have a continuum, which means this hook has an infinite number of degree of freedoms. And if we would take the PDEs, we were not able to solve this equation. But what we are doing in the end, we are splitting up this continuous domain into discretized simple geometrical shapes, which we call elements. You cannot see it here on the right side. And in the end, a finite element, and that's where the name comes from, is nothing more or less than a small piece of a structure. And the good thing is that now we can solve this equation for every of the small structures. And if you take a look at the structure at the element, we have nodes at the corners. And in the end, nodes are connecting the different elements together. And if we take a look at what we have to do in order to run the FEA simulation, we have some steps. First of all, we have to discretize the continuum and select so-called interpolation functions. We need these interpolation functions for a very special reason. If you take a look at this hook here, and let's say we will use this finite elements and replace the continuous domain by a discrete domain, we are only solving, let's say, stress, displacement, etc. for the elements. And therefore, we somehow in the end need to interpolate, and that's where we need this interpolation functions, but we'll talk about this in 5 minutes more in detail. And the other steps, like finding element properties, assemble element equations, solve the global equation system, and in the end compute additional results. These are steps which come after these, and meshing is really the very first part of your finite element analyzers, because in the end, if your mesh is not good, all the other steps will maybe useless. And to understand what meshing basically does, let's take a look at this very simple example. Let's just imagine we have this one-dimensional beam where we're applying an axial load. And this beam is defined by its length, a force which I call P. You can also think it's a pressure. In the end, it's the same if we calculate it. And instead of using this continuous structure, we will replace it with finite elements. And therefore, we will use a one-dimensional system. So we have only we can have only one dimension, actual dimension. And here we will replace this bar with, as I mentioned, with elements. You can see here we have the nodes. And since we're using a one-dimensional case, we only have nodes. and the elements are described by a line only. And now let's take a look back at what we learned during university, because I think you may saw this is a very simple case for mechanics, and try to, how can we consider the elastic bar? And basically in this one-dimensional case, we just need the length, the elastic modulus of the bar, as well as the cross-sectional area. And if we now take a look at, for example, the first and second node, we only have a deformation or displacement in x direction, which I called u, and a force acting on the node called F. And we can now take the equilibrium of forces and moments to write down or to express these forces. And if you take a look here, in the end we say that we have a factor which is made of A, so the cross-section multiplied with the Young's modulus divided by the length. And we say that the deformation or the displacement between U1 and U2, between the first and the second node multiplied with this prefactor, is the force. And we can do the same for the second node. And if you take a look at this equation, it will remind you maybe to this equation of Hooke, which was used to describe springs, and it's pretty much the same. In the end, we are saying that displacement multiplied with stiffness is a force. And if we now apply this formula on both nodes, we have basically a finite element model. And just for you to understand why this is a force, take a look at this constitutive equations which you might know from university. So in the end, what we have here is nothing more or less than a force, because if you replace u, for example, if you replace the things here in the equation, you will get to the forces. And this derivation is very nice described on a YouTube video, which you can find here. And I will also post the link of this video to the forum later, so in the case you want to take a look at it. And if we take now a look at these two equations, we can write them a different way, like this. Now it's looking much more complicated, right? And this is basically a very simple FEA model, as I mentioned. Because if we take a look at this equation, we have displacements here, the forces here in our own vector, and here we have a matrix. And right now what we can do is to write it in like this, and then we have here the stiffness matrix, which is depending in the end on the nodes and the material properties. We have the nodal displacement vector u, and we have the force vector F. And in the end, F, we know F is based on our boundary conditions. K, the stiffness matrix, in the end what we create when we do meshing. And this one, U, the displacement vector, this is unknown. And this is what we try to find out when doing a finite element analysis. And the very good thing about this simple example is that we can here do both. We can calculate the exact analytic solution as well as the finite element solution. And here you can see the comparison. So in blue, you can see the exact solution, which you can calculate for this very simple case. And in red, you see the numerical solution of the finite element analysis. And first of all, you should consider we only have a solution for the red points, only for the nodes. But if you take a look, it's basically very accurate. The curves are laying over each other. And this shows a very simple way what's the big strength of finite element analysis. But there are some things we have to consider, because we cannot take the solution without taking a look at it and try to understand what basically is happening. The big difference between the analytic solution and the finite element solution is that the analytic solution is defined for every point in the range of X, while the finite element solution is only defined in the nodes. And if you take a look at this chart, it's basically showing the strain instead of the displacement now, which we can calculate out of the displacement. And while the exact solution is giving us an analytic function of the strain over the length, the finite element solution will only give us averaged strain for every element. So, and this is the big, let's say, source of errors. We cannot expect the same things from an analytical solution like we do from a finite element solution, and the other way around. And if you take a look now here, you will see that we are facing with another problem. I mean, we have the values for the nodes or for the elements, but we don't have any information what is happening in between. And therefore, we are using so-called shape functions to interpolate the solution between the discrete values obtained at the mesh nodes. And this is, by the way, the difference between first and second order meshing, which we will talk about later. But basically what we're doing in the end is interpolating what is happening here in between. And if we now take a look at the general FEA process, I mean, let's try to take the perspective of a user. And in the end, what you want to do is solve a problem. You want to understand something, for example, the behavior of a part you have designed, or you want to improve something. And if you use the FEA analyzers, you can divide this process into several steps. First of all, you have a physical problem. The physical problem can, for example, be the hook we talked about. The physical problem can also be the bar we talked about when I showed you what is the idea of finite element analyzers. And based on this physical problem, we create a mathematical model. This mathematical model is very much related to our meshing. So we are converting this continuous problem into a discrete problem. And once we have this discrete problem, we use numerical methods to solve it, because the example I showed you was very easy. But there are also some other examples where you cannot just solve this linear equation system so easily, and there you need numerical methods. And in the end, what will happen is, at the end of the day, we've done our simulation, and before we use it, we have to make sure that the result makes sense. And there are two options. The first option is that everything is fine. You take a look at the results and they make sense. What means make sense? Good question. First of all, make sense in our case means that the results are in range, so that there are the range, for example, of stress and displacement is in a range we know and which makes sense, but also other criteria can be used to make sure if a simulation makes sense or not. We will talk about this especially in the last session in 2 weeks. And in the case the answer makes no sense, there are a lot of reasons. And first of all, it makes no sense. The reason can be that we need to make design improvements or change the problem. To give you a very simple example, just imagine you have designed something which should work under linear elastic material behavior, and your simulation crashes. Then one reason can be that your current load case is outside this linear elastic behavior. This would be related to really a physical problem where we have to change the physical problem or the simulation type. Another problem can be related to the mathematical model itself. For example, the results are looking very coarse, and you have like high jumps in stress. And then we need to refine and improve analysis and improve our mathematical model. And that's what we're going to do today. We will talk about how to improve our mathematical model, especially how to choose the right mesh for your own analysis. And When we're going to talk about meshing, it's very important to understand that meshing is not only about creating a mesh, but also it starts much more in advance. Basically, meshing starts in your CAD system. And just imagine you want to simulate assembly like this. And if you take a look at the, let's say, productive CAD files, which are used by the designers and engineers, you will find a very complex assembly made of several thousand bodies, having a lot of short edges, small faces, and which is very hard to handle and also to mesh. And in the end, what we want to achieve is a much reduced model, which has a good model quality, so we don't want to deal with short edges, small faces, etc., and which is simplified as much as possible. And let's just quickly go through the most important steps of CAD preparation, just to make sure you all know about it, and also because it's really important. In the end, you can save most of the time for mesh generation having a good CAD model. And first of all, the first part is simplification. And why do we need to simplify? First of all, it makes your meshing faster and much more robust. The second very important reason is that you need a fewer definition of simulation setups. Just imagine if you replace a lot of solid bodies by fewer one, by fusing them, you will also use a lot of contacts and parts where you have to define materials. Another problem, which is another advantage is, for example, you have faster solution times. Your mesh is smaller, you will have less contacts, and overall you will save a lot of time and resources. And finally, which is also very important, it will improve everything related to post-processing for you, because you will have smaller mesh and smaller result in the end. So there are a lot of reasons to simplify a model. And the first thing you should really ask yourself when preparing such a simulation is, which parts do I need to simulate? In this example, which is very good, I think, you can really see that we have a lot of parts, and it would be a huge mess to simulate everything. But in this case, only this beam here is relevant, let's say, for the overall structure behavior, and therefore we will only simulate the critical parts, because this is the only part where we think it could fail. Another trick which I really recommend, and which is very easy, is to take advantage of symmetry. In this case, for example, we have a symmetric case in two directions, in this and that plane. And therefore, we can just, instead of simulating the whole part, we can just simulate 1/4 of it, which will save, even if we have the same mesh size, we will save 75% of elements and therefore 75% of computing time. Another very important step in geometrical preparation is the so-called defeaturing. And this bolted joint is a very good example. In this simulation, for example, we want to analyze the structural behavior of this assembly under load. And what we know is that the bolted connections are very strong. And we do know that if this part will fail, it will not fail at the bolted connections, but somewhere else. And therefore, we just defeatured the bolt joint, just fused these two parts. And this will save a lot of work for us, because first of all, we are saving 3 contacts, or even more, 6 or 7 contacts here, which we have to define. But also, and that's another very important reason to do the featuring, it will make the meshing much easier, because we don't have the small holes here where we need extra refinement, etc. And this is another very important thing, is to merge and split faces the proper way. And this is a very good example to understand why. This is not related to meshing all the time, but also to simulation setup. Just imagine you have this protection of a truck, and you want to simulate an impact at these points. If you would not split the face into these three subfaces. You could not apply a boundary condition because you want only have an impact here, here, and here. And therefore, really the first step, as I mentioned, is to prepare the CAD model and really think about what you want to do. In the best case, you should have the whole simulation set up before your eyes and then start to prepare the CAD model. And the last thing you should consider is related to simplifying. It's fusing solids. For example, in this case, when we're not interested in the joints between these parts, just fuse everything to one single solid. And yes, again, following these ideas allowed us to massively reduce the model complexity and was the first very important step towards a successful simulation. Yes, and after we have simplified our model, we need to prepare a mesh. And this is a very important point because our biggest problem is that we are facing a trade-off here. On the one hand, we want to have a very small mesh to reduce the effort for us, to reduce the computational resources which are needed, to reduce the time which is needed to prepare the simulation. On the other hand, we want to make sure our simulation results are of high quality, because in the end we want to use this result to improve a product later on. And the quality of a simulation is very much related to the right mesh size. And having a two-course mesh can really create serious problems. Simulation will work a lot of times, but the results are crap. And therefore, a very good starting point for a simulation is a so-called convergence study, where we try to obtain a mesh-independent result. And mesh-independent result means that in the end, the result of our simulation should not anymore be depending on the size of our mesh. So in the end, we want the mesh with the fewest number of elements possible, which still give us the right stress at the chosen point. And it's a very good way to make sure your results are also good, to take a look at the stress on a single point. And therefore, what we will do, we will start with a, let's say, coarse mesh, analyze it, make it finer, and compare the results to the previous mesh. And we will do this loop until the results are not changing anymore. And then we will just take a look, where do we have high stress, where do we have low stress, and then we can decrease again the number of elements in areas where we have less or low stress and displacement. And this is a very good example. Here we just took, you can see this structure. And first of all, we did a first order very coarse mesh as a starting point. Everything was chosen as simple as possible. And then we created the simulation, run it, and then we increased the global cell refinement. So, and this is very important. We had nearly the same mesh size at the whole part. And here you can see how the maximum Farmese stress changed with increasing degree of freedom. So degree of freedoms in this term is related to the number of elements. It's basically the number of nodes. And here you can see at the beginning we have a high change, but between in the end the fine and the very fine mesh there is a very small change, and which means that our solution here is mesh independent. But if we take a look at the results, we will see that we are wasting a lot of cells somewhere where we don't have a lot of changes, a lot of stress. So what we can do is go a step back, use a general causal mesh, but refine the mesh where we have high stresses and displacements, like here. And if we use a coarse mesh with local refinement, we only have 11,000 degrees of freedom compared to 500,000 for the very fine mesh or 225,000 for the fine mesh, but still the results are in range. And this is really a very good example for mesh convergence, and this is the first thing you should do. If possible, start with your geometry, use automatic meshing, increase the meshes until you have a much too fine but mesh independent result, and then go a step back and try to use the coarser mesh and improve it with adding local refinements. Yes, I hope you enjoyed this kind of introduction to meshing. And after we have talked about, let's say, the most fundamentals of meshing and the FEA process in general, let's went together through the meshing options of SimScale for finite element analysis and discover all the different functional capabilities. And if you have a question, just write it in our question window and we will try to answer it as fast as possible. And just because some people say that they have problems with a network connection, you can also watch the recording later in the case it should not work at all. First of all, let's take a look at the SimScale platform. And at SimScale we have a lot of different options for meshing. Therefore, let's take a look at this project I have prepared, which includes a bike frame. And first of all, let's create a new mesh, call it mesh 1, select the geometry, and now we can add a mesh operation. And here basically you see all 4 mesh operations which are available on SimScale. And for FEA, we have this Tet-Dominant Meshing, which is the only measure supported for FEA. So the other ones are only for CFD as mentioned in the description. And this Tet-Dominant measure is called Tet-Dominant measure because he's using tetrahedral elements to discretize the continuum. And it can be used for FEA and CFD. And basically you have control over everything. There's only one restriction for the Tet-Dominant measure. The Tet-Dominant measure can only handle solid body geometry, so step files, IGES files and BREP files, but no STL files. And here you can see some examples which demonstrate how powerful this meshing tool is. For example, on the left side you see stress analysis of a global valve where we mesh different parts with different refinements, so you can see all the bolted connections were meshed with a very fine element length, while we use the coarser mesh for the valve body itself. It can also be used for fluid flow simulations, like here where we have a simple pipe system. And now let's went through the different options of the Tet-Dominant meshing to understand how we can control the mesh. And first of all, if we're going to create such a mesh and choose a Tet-Dominant measure, the first thing we have to choose is how we want to do the element sizing, so how we want to define the size of the elements. There are 2 options. The first option is to use automatic element sizing. And automatic in this case means that you only select a global mesh fineness parameter between 1 and 5. And based on this, the mesh is automatically created. And as you can see here, if we use automatic element size, we have nearly the same element size for the whole models. There will be some automatic adaptations, but in the end we have a constant element size, which we can not directly control. And for a lot of cases, this kind of meshing is good enough, especially when we do a mesh-independent study. But from time to time, when you want to have more control over the global mesh size, you can also do manual element sizing. And there we use 3 parameters to describe the element size. We have a minimum element edge length and a maximum element edge length, which are giving the bounds for the element size. So here's a very good example. In this case, min element length was 0.0 meter, so 7 centimeter, and the max element length was 0.29 meter, so nearly 30 centimeter, and the measure is automatically adapting the element size based on the geometry, the proximity, etc. within this range. And you can control like the growth between the different element sizes based on just mesh grading. So on the left you can see mesh grading of 2 and here of 0.2, which 2 means in the end you have 200% growth. In contrast to that, 0.2 means you have 20% 10% growth between elements of different sizes. And this is massively influencing or impacting the whole mesh structure, as you can see here. So by just changing the mesh grading, we kept, let's say, the minimum size and the maximum size of the mesh, but we have a much smoother mesh. And you should not forget, a smooth mesh is very important because if your growth is too high, this can lead to numerical problems during the simulation. And just to make sure you got everything, so here we can use automatic mesh sizing, choose between the different mesh finite levels, and we can also change to manual mesh sizing, where we define the minimum maximum edge length manually as well as a mesh grading. The next option you will see is a quadrangular surface elements option. And to understand what this means, the measure is called Tet-Dominant Meshing, not Tet-only measure, which means we are creating mainly tetrahedral elements, but we can also create quadrangular elements. And this is an option you can manually turn off or on. So here you can see the same mesh settings. The only difference is that on the left side we turned quadrangular surface elements off while we turned it on for the right picture. And basically what is happening is that the mesh is also using, yes, quadrangular elements on the surface. And this has some consequences. First of all, this will enable pyramidal elements also to have a transition between the tetrahedral and the quadrangular elements. And the reason why we should use these quadrangular elements is that in theory, quadrangular elements give you a better result quality, but on the other hand, they are less robust. So it's a trade-off every time we have to decide. Using only tetrahedral elements means our meshing will be more robust, while if we want to increase the result quality, we should also use quadrangular surface elements. And in general, start without this kind of elements, and for some special geometries it can help, and there you should try to enable this option. But in the case you go into meshing problems, especially if you got error messages like negative volume, or if the meshing just failed, you should disable this setting. And here you can change it from true to false. Okay, and another option you may saw is second order elements, and this is related to what we talked about at the beginning when I said that we basically only have a solution for the nodes and have to interpolate in between them, or for the elements. And on SimScale we have two kinds of elements, first order and second order elements. Both of them are tetrahedral elements. The first order elements, which are chosen by default, have only 4 nodes. So we have in every corner of the tetrahedral a node, and therefore we have degrees of freedom in X, Y, and Z. A second order element comes with additional support nodes at the middle of the edges, which are connecting the sides of the tetrahedral. So we have, instead of 4, we have 10 nodes. And we have the same degree of freedoms, but in the end we are not interpolating linear between the nodes, but we have a quadratic function. And therefore it's a very problem-dependent choice of the mesh. For problems where we have contacts, the first order elements perform much better than the second order elements. And everywhere where we have, let's say, high deformations, the second order elements perform much better than the first order elements. And the reason for this is that second order elements have more degrees of freedom with every element than first order elements. So if we have large deformations, we cannot approximate the changes between nodes with only a linear function. And there this second order approach of the second order elements helps us a lot. But everywhere where we have contacts, the first elements perform much better. And one thing you should keep in mind, if you choose second order elements with the same mesh refinements, you will get maybe the same number of elements, but much more nodes and degrees of freedoms. So therefore you cannot compare a first order mesh and a second order mesh just because they have the same refinement settings. And in general, second order mesh will take much more time to calculate and also to solve later on compared to a first order element mesh. And a very good example you can see here, it was the study which I think was done by our power user Ben Lewis, and he just took this very simple example and used three kinds of mesh. He used a coarse mesh first order, a fine mesh first order, and a coarse mesh second order. And if you now compare the results on the right side, we have the same load case for all three. You can really see that there is a big change between the coarse and the fine mesh for the first order mesh. And the reason is for sure that the coarse mesh is not able to solve all the high stresses and displacements which are happening here. But if we use a second order mesh with the same mesh size like the coarse first order mesh, the results are looking completely different because we have second order elements which are interpolating also in second order. And therefore second order mesh can help us to save elements or even to save nodes in the end. It's just a question of the right application. Okay, and independent from this general mesh size we are defining here, we can also add refinements where we can really define the element size for phase or volume. For example, let's take here moderate mesh, save it. If you go now on refinements, you can add these refinements. And the image here gives a very good example how you can use refinements. For example, here this is a simulation where we have a bolted connection between two plates, and we used mesh refinements for the bolt in between them to ensure that we have here where we have the contact and also where we have a lot of changes that we have here a right mesh size. And the very important thing about this mesh refinement is that it allows you to increase your mesh efficiency. If you remember at the beginning, I showed you this mesh independent study where adding a local mesh refinement helped us to reduce the mesh size massively for a mesh independent solution. And in the end, you can define these mesh refinements for particular phases or solids, and then you can control for these entities the element size as well if you want rectangular surface elements or not. So for example here I can just, if I for example expect to have high stresses here, I can for example just select this face here, this face here, and this face here, and this face here. I can add the faces and then define again the element size. And again I have here minimum, maximum element length and mesh grading. So the only thing I have to define globally is if I want to use second or first order elements. And if you go on save, this mesh refinement is applied. Okay. Then let's move on with a live demonstration to try to utilize the knowledge we've gained during the last 45 minutes. And what we will do today, or what I will do, I will first of all show you how you can create such a mesh independent study on your own. We will take a look at the results, and then we will talk about your homework assignment, which is very much related to this live demonstration, so please listen carefully. Okay, and therefore I have prepared another project. It's basically the same geometry, it's a bike frame, but to save some time I have already prepared everything. So here we have the geometry of the bike frame, and here you can already see some very important steps which were performed, I talked about when we focused on CAD preparation. So as you can see here, first of all, it's a symmetrical model because we have a symmetric load case, which saves us half of the elements and half of computational error. And also, if you take a look at the frame, it's very simplified. So we have removed the very small lofts here and just made sure that this model is as simple as possible. And what I did then, I just created a first order mesh, very simple. And after that, I just copied the mesh like this. You can then, for example, change the name to first order fine. And then I just change it here to fine. And this is very helpful, especially if you have more complex meshes, that you can just copy and reuse the mesh setup. And first of all, let's take a look at the case. So what we're gonna investigate today is that, just imagine we have the model is fixed here. So we have fixed basically two things. We have fixed first of all the back of the wheel and the wheel fork here. And then we can just add a load here. And then what we want to find out in the end is the stress distribution inside this frame. And yes, you can find this here. So just to show one of the setups. So after I have meshed this, I just defined the analysis type. It's a static analysis, and we used advanced one to have more control. Then I just had to define the material I want to use, in this case aluminium, which was which I took from our material library. And then we had to define the boundary conditions and the loads. So first of all, we have a constraint here for the rear wheel. So this faces cannot move, and they are defined by a external point, which is a rotation axis of the rear wheel. We did something very similar for the wheel fork here. No displacement in any direction and a given external point. And we added the same for the symmetry here. We just choose this as a symmetry plane. And then we finally had to add a load. In this case, it's the weight of a sitting person. So 400 newtons, which is around 40 kilogram. And since it's a half model, it's related to 80 kilogram weight of a person. And then the only thing we had to do is we added some result control items here, which are calculating during the simulation, for example, minimum maximum von Mises stress, minimum maximum displacement, and minimum maximum strain. And then we just run the simulation. And once the first simulation here with the first order medium mesh was finished, we can take a look at the results. And don't forget, everything we do here is in your web browser. And sorry, I just clicked the wrong button. And yes, this is my result. And now, for example, we can take a look at the displacement, or if we want, at the stress. And as I mentioned, in the end, our question is, if the stresses which we will get right now are mesh independent. And the easiest thing to check this is to take a look, for example, at the minimum maximum for meso stress. And for this simulation, the maximum for meso stress is not very high. And if we take, for example, now the mesh, here we have 9.6 million Pascal. And if we take a look, for example, at the very fine mesh, first order very fine, it's 16 million Pascal, a very high change, right? So this means something is wrong with our coarse model. And if we, for example, further increase the mesh size using a second order model, you will see that we still have a change for the maximum stress, but it's much smaller. Now we have 70 million Pascal. So which shows us that a very fine mesh somehow is fine enough for solving the highest stress. But if we take now a look, for example, at this very fine mesh here, first of all, let's take a look at the stress. And if we now show also the mesh size, the mesh, you will see that this mesh is really, really fine. I can zoom in and still we cannot see any mesh structure. And now we can see it. So this is the mesh size. And for example, it's really small. I hope you can see it. And everywhere where we're expecting high stresses, like here for example, it makes sense, but everywhere else where we have nearly no stress or no displacement, like here, like here or here, it's much too fine. And so what we can do right now is go a step back, use the coarser mesh, and add local refinements everywhere where we see a high stress. And this in the end will help us to receive the smallest possible mesh independent solution. Great, and yes, I hope you have a lot of questions because we're starting our Q&A session in some minutes. And finally, I would like to show you your homework for this week. So we will provide you with this kind of model, and your job is to decrease the degrees of freedom by adapting the local mesh size using mesh refinements. And therefore, you will find on simscale.com our forum, there you will find a post called FEA Master Class Session 1 Homework, where you will find step-by-step description how to refine the mesh. And I will send you a link to this tutorial and also to our recording of this session tomorrow, when you can just go there, import the project and do the homework on your own. And yes, I'm really interested to see your results. And once you finish the homework, just submit it using the form on simscale.com/FEA Masterclass. And by submitting all 3 homeworks, you will get certified by us. Great, and now we have some time for our Q&A. So I hope you have a lot of questions and we can go through them. Okay. First of all, yes, first question is by Brian, and Brian wants to know if I can explain or perhaps show the difference between linear and nonlinear strain when choosing results in SimScale. Brian, yes, for sure. Let's take a look at this. By the way, we will talk about strain and linear, nonlinear material behavior next week. But basically, the difference between nonlinear and linear strain is how this part will behave after you remove the external force. And therefore, let me try to give you a easy explanation. Just 1 second. I need my painting tool. Okay. Well, let's say we have this probe here, and we are applying a force. And okay, and if we increase our elongation and we would measure the strain, it would look like this, linear at the beginning, and then at some point it will look like this. And here we have linear material behavior, and here we have nonlinear behavior. And let's say, as long as I am inside this linear behavior of the material, when I release the force, the part will go down and we will again here. But if I am inside this nonlinear material behavior and I have plastic deformation, and even if I remove then the external force, I will not go back here, but I will end maybe somewhere here. And this difference, this is because of the plastic nonlinear deformation. And so, and if you don't end here, but here, you have remaining elongation, remaining strain, and this is the nonlinear part of your stress. Hope this answered your question, Brian. I see we have some more questions. Okay, let me go through them step by step. Next question is by Hossein. If we have already solved the problem using a very fine mesh, why then we are getting back to a coarser mesh, fine mesh only on peak points? We have already paid the price. Hossein, that's a very good question. First, good news is you don't have to pay any price since SimScale is free, but let me answer your question. You're right. In theory, if I just increase the global mesh size and have a very, very fine mesh which is mesh independent, my problem seems to be solved. But you should not forget, in reality, a lot of times you want to perform like a parametric study with the model, or you want to test several conditions. And then if you use a too fine mesh where you wasted elements where you don't need them, every time you have to pay again this price for the computation. And therefore it is recommended to use a mesh which is as small as possible. And what you should also not forget, as more cells you save where you don't need them, as more you can spend where they're really necessary. For example, if you found out in the regions which are important, you can even increase the mesh size there a little bit more. Michael wants to know, will you be showing in future sessions the nonlinear behavior of material, stress beyond the yield limit, failure mode analysis? Michael, yes, or Michael, exactly this is what we will do. Let's us take a look just at our curriculum or syllabus for the FEA Master Class. And then you can see what we'll do. So next week we will talk about material nonlinearity, and there we'll talk also in detail about different material models, how to model nonlinear behavior, and how to understand if a part fails or not. Constanios has a question. To be sure I understood the task of the homework. The goal is to change the mesh. Will it be generated in this model that will be given us in order to have less degree of freedom? Yes, exactly. We'll provide you with a ready-to-use mesh, and where you have a mesh, the related simulation, and your job is to take this mesh and to adapt the mesh size in order to reduce the degrees of freedom by keeping the quality of the results. Next question is by Hamza. One more question. Is there any possibility to have numbers of DOF of a simulation in SimScale platform? Or could you please let me know how can I compute the number of DOF in a mesh FEA simulation? That's a very good question. It will be described in the tutorial, but let me show it you quickly. Once you have finished your mesh operation, you will see the overview here. And here you can exactly see how many elements were generated and how many nodes. And the nodes, these are your degrees of freedoms here. Ode wants to know what is a good start number of cells for any model. Ode, first of all, it's very hard to answer this question because it really depends on the problem. If you have a simple elastic bar, you may just need several hundred elements, while if you're simulating, let's say, a complex assembly, for example, a crankshaft with springs and everything, you will need several hundred thousands. In general, this is very much related to experience, but I would start with a mesh which is as coarse as you think it can be, and then improve it step by step. Okay. I already got some Brian wrote me that what he would like to talk about next week, guys. If there is something related to material modeling which you really would like to find out, just reach out to me, sending me an email, mmurphy@simscale.com, and we will try to talk about everything you're interested in. Then the next question by Aravind is, what is the maximum mesh elements that SimScale can handle? This really depends on the kind of elements you're using and also the machine. If you take a look under the options here, you can choose the number of computing cores. And every computing core comes with additional memory. So we can handle in the end several million degree of freedoms, but it really depends on your model itself. Jörg wants to know how we half-size the model. Jörg, right now SimScale is coming only with limited number of options for geometrical processing. You can do, for example, scaling. You can scaling or feature detection. If you want to prepare the model, you should do it in your CAD system before importing the model to SimScale. And what we can also recommend is to use Onshape, our partner company, which is offering a free-to-use online CAD system. Okay, we have some more questions. Let me try to answer all of them. Okay, John wants to know what's the best file type for FEA. John, as I mentioned, we currently support 3 file types for Tet-Dominant Meshing: STEP, IGES, and BREP. And from my personal experience, I would suggest to use STEP, which seems to be the most robust file type for geometry import and export to SimScale. Okay, seems like all questions are answered. In the case you have a question which we didn't talk about right now, you can also write it into our forum and then we will answer it. And great. There's the last final question by Aditya. He wants to know if second order mesh uses a quadratic function for interpolation. If there is something higher, maybe a third order mesh. Yes, this is available in theory, but right now at SimScale we only have first and second order elements, which should be enough for 99% of all engineering problems we have. Okay guys, perfect. Thank you very much for joining us today. It was a big pleasure for me. And yes, this was just the beginning of our journey. So next week we will really go more into, let's say, hands-on things about material modeling and predicting failure. Hope to see you all next week. I will send you an email tomorrow with all the resources you need to do the homework. Yes, I wish you a very nice week and hope to see you soon. Have a nice day. Bye.